It's really great to be out here at Stanford today. As you probably deduced, I'm not Dr. Danielson. Unfortunately, he had to be called away last night on short notice for a family emergency, and so we wish him a speedy journey to be with his family. As many of you know, Dave was the architect behind setting up this event, and he did so because he felt that we shared a lot in common between Stanford and the Department of Energy. And just scratching the surface, first and foremost, we share the company of some of the most innovative minds, scientists, technologists, and entrepreneurial thinkers on the planet. And as we saw earlier in the presentation, we share a love of acronyms and logos. And so, as many people at DOE know, I'm becoming quite the expert on navigating trademark infringement in my pursuit of the perfect logo. I'm very thrilled that we have a great group of leaders here from the Department of Energy today that represent a broad swath of our department activities, including a few Stanford alums who jumped at the chance to return to their old stomping grounds. And so I just want to give a little shout out to each of them. And if you're here, if you could raise your hand and just stand up for a moment. We have Ken Alston, who's the special advisor for finance. We have Margaret Schaus, who's a senior policy advisor in EERE. We have Jay Fitzgerald, who's a technology manager in our bioenergy department and who's a man after my heart on synthetic biology. I also want to recognize that this is a revolving door that works both ways, and we have members of our EERE family who have since gone on to return to Stanford and pursue their academic careers here. And so we have Greg Stillman, who worked at EERE for 5 years as a technology manager in the geothermal office, who is currently at Stanford pursuing an MBA and an MS in environment and resources. And then Darren Hondoko, who was a summer intern in the geothermal office a few summers back. He's now an undergraduate senior pursuing a BS in material science and engineering and is also a member of the Stanford Energy Club. And then lastly, we have Catherine O'Malley, who's from the fuel cell office, who is also at Stanford and is here today, I think, in the room right now. I'm not sure if you can raise your hand, but okay. And so we hope to continue this revolving door because solving our climate and energy challenges are going to require that we recruit and retain the best and brightest talent to join us in this work. The Obama administration has made it a key priority to engage students through STEM education, and we're here today to actually try to poach as many of your top performers as we can, so keep that in mind. I do want to say special thanks to Sally Benson, Arun Majumdar, and to everyone at Stanford and at DOE who made this day possible. DOE is very proud to have Stanford as such a strong partner in our efforts. The Precourt Institute for Energy here on campus has just recently joined MIT in supporting the implementation of DOE's Clean Energy Education and Empowerment Program to advance women's participation in leadership and in clean energy. We absolutely need to be closing the gender gap that persists today in the clean energy field because it's going to be one of the most dynamic industries out there over the coming decades, and we're going to progress farther and faster if we're drawing on all of the best and brightest minds that we have. I'm here today to set the stage by providing you the big picture of what EERE is doing to tackle our energy challenges and some of the exciting technology developments for all of you fellow clean tech lovers, and also to really open up a discussion on how we can continue to work together in support of building a robust pipeline of R&D for clean tech economy that we're helping to build. And so the cornerstone is our network of 17 national labs across the country. These places are national treasures where real cutting-edge research is underway, and that includes 3 that are here in California, including, of course, SLAC's National Accelerator Laboratory, which we'll be touring later on this week, which has done so much tremendous work in partnership with the university. We're working hard to help our labs accelerate the rate at which their technology reaches the marketplace and gets into commercialization. And so this is especially an exciting time to be at DOE because we're at the forefront of what are really defining issues of our time, leading the transition to a global clean energy economy as well as fighting climate change. The numbers can be really scary. We have about 7.3 billion people on the planet today, and the UN estimates that we're going to balloon up to 9.7 billion people by 2050, which is represented here by the little red figures that you see on the map. But really, it's about the 33% growth in population over the coming years, with the majority in developing worlds who are hungry to live the kind of lifestyle that we've become accustomed to here. And that means a whole lot more energy usage. At the same time, our top scientists are telling us that we need to be able to reduce greenhouse gas emissions by up to 80% by 2050 to avoid the most devastating impacts of climate change. There's no longer an abstract threat here. 2015 was the hottest year on record ever. Fortunately, we've had some landmark news in November when President Obama and other world leaders pledged to double their nation's investments in clean energy technology through an initiative called Mission Innovation. They recognize that the only way we're going to solve this problem is to innovate our way out of it. And that includes inventing some of the technologies that have yet to even be thought up. And so we're at the center of building the clean energy economy that is emerging. And in fact, we are the single largest funder of clean energy innovation in the world to the tune of nearly $2 billion annually. We lead DOE's efforts to develop and deliver market-driven solutions for energy savings homes, buildings, manufacturing, sustainable transportation, and renewable electricity generation. DOE recently released a report called Revolution Now that details the progress we've seen over the past 7 years on a range of clean energy technologies that are all starting to reach cost competitiveness. You can read the full report online, but I'm just going to give you an idea of the progress by highlighting a few little facts and statistics here. The U.S. reached 6 gigawatts of wind power capacity. Wind accounted for 31% of all new generation capacity installed in the U.S. from 2008 to 2014. Solar costs have dropped 60% since 2008, and U.S. solar installations have grown 25 times over that same period of time. Utility-scale solar PV grew by 68% in 2014 to 9.7 gigawatts total. Over 99% of this has been installed since 2009. Distributed solar PV has over 8 gigawatts installed by 2014, equal to the capacity of 16 coal-fired power plants. And we have nearly 78 million total LED bulbs installed through 2014, which is a 6-fold growth since 2012. And then lastly, we have nearly 300,000 EVs that have been sold through 2014. I believe it's more than 400,000 on the roads now. And while that is short of the million target that we have for 2015, we do believe it's through these efforts and these targets that actually have driven the adoption of the numbers that we have today. And so while there's been terrific progress, we still have a long way to go to hit our target of reducing emissions by 26 to 28% by 2025. We need our tech at scale in 2050, as it can take up to 20 years to go from prototyping to having technology into the market. And we need to fill this R&D pipeline between now and 2020 like never before. Fortunately, we have a long-term climate policy landscape which has emerged under President Obama's leadership. The Clean Power Plan is focused on reducing greenhouse gas emissions by 32% in the power sector by 2030, and CAFE standards are set for doubling fuel economy by 2025. We are seeing major results here at EERE. A group of external evaluators assessed our R&D portfolio over the past several decades and determined that a total taxpayer investment of $12 billion has already yielded an estimated net economic benefit of more than $230 billion. So $12 billion in and $230 billion out. That's an overall annual rate and return on investment of more than 20%. And I'll take those results, as I can imagine an investor would, any day of the week. The central question that animates each of us each day is what's next? What's around the horizon? We're always looking around the curve for the next technologies that we need to support. A big push within our Vehicle Technologies office is on batteries, which have the potential to become major game changers. It's an exciting time for batteries, at least if you're an energy geek like myself. Improving battery performance is, of course, a major key towards improving performance and increasing adoption of plug-in electric cars, and so this area of technology has a major multiplier effect. The production of batteries for energy will soon surpass batteries for consumer electronics. We've seen an amazing drop in cost in recent years due to new higher energy dense materials and increasing manufacturing scale, like we're seeing with the announcements of things like the Tesla Gigafactory. DOE has been investing in lithium-ion battery technology innovation for almost 20 years. If you need some beach reading or some reading material for your vacation this summer, you should pick up Steve Levine's book, The Powerhouse, which recounts a lot of the successes that DOE has had in this area, as well as the battery development efforts at Argonne National Labs. Through DOE partnerships with companies like Amprius, NVIA, LG Chem USA, who are using silicon-based anodes and materials from Argonne National Lab to create some of the best batteries on Earth. As a matter of fact, we've seen more than a 70% reduction in the cost of lithium-ion batteries as a result of our efforts since 2008. DOE has also worked with a company called 24M to develop a revolutionary new semi-solid flowable battery electrode material that consists of small particles of traditional lithium-ion battery material that could cut the cost of batteries in half. This was developed with about $5 million in support from the Department of Energy. This new flowable battery material has amazing electrical and ionic conducting properties that allow the electrodes to be much thicker, which cuts the amount of inactive material by more than 80% and increases the energy density up to 40%. With this tech, you can imagine a future in which your battery is done and you can swipe out to a new semi-solid electrode with the best material available. And over the long term, you can actually imagine a world in which our cars can pull up and have a semi-solid electrolyte or electrode battery fluid swapping station to bring you the best and latest chemistries for your battery. We've implemented a major initiative on solar called Sunshot, just like President Kennedy called for a moonshot to fulfill his vision of a man on the moon within a decade. President Obama called for a major effort to make solar energy fully cost competitive with other forms of electricity by the end of the decade. Our Sunshot program has encouraged innovation and development of new jobs in solar throughout the country. We're only halfway to our goal through this decade, and we're already about 70%, we're only halfway through the decade, and we're about 70% towards our target on the Sunshot initiative. Since 2008, the cost of photovoltaic PV cells have dropped more than 60%, and US PV capacity has grown nearly 25-fold to more than 20 gigawatts. As President Obama recently noted in his final State of the Union address, solar is saving Americans tens of millions of dollars a year on energy bills, and is actually employing more Americans than ever than even the coal industry in jobs that pay better than the average, according to findings from the Solar Foundation. In the area of enhanced geothermal systems, or EGS, we also believe could be a game-changing technology for clean energy, providing large amounts of renewable baseload power to support high penetrations of intermittent renewables like solar. This is a true sleeper technology. We predict that in 15 years from now, we may be talking about the EGS revolution in the same way that we talk about the shale gas revolution today. Several members of our geothermal team will actually be here on campus. In fact, we have some of the key people here today. Next week for a Stanford geothermal workshop to share more of the focus in this area. The Earth has vast thermal resources about 2 to 6 miles beneath the surface, with more than 1,000 plus gigawatts of resources available if we could just tap into it cost effectively. They're deeper than oil and gas, often laying beneath some of the hardest rock known to man, where there's no existing water or permeability for water flow. And so the key technical challenge we have is in developing lower cost and faster drilling technologies to access the resources and creating the fractures in the rock to allow fluids to flow. And so our flagship effort over the next 5 years to accelerate deployment of EGS is through our Frontier Observatory for Research in Geothermal Energy, or FORGE effort. This revolutionary endeavor involving the first dedicated field site of its kind will enable cutting-edge research for drilling and research into drilling technology and testing, as well as allowing scientists to identify commercial pathways for large-scale and economically viable EGS to the tune of over $170 million over the next 5 years. We're throwing all of the innovation that we have at a single site with pioneering breakthroughs like the first ever horizontal EGS well, which dramatically increases the productivity and reduces cost. One of the most exciting young companies that we're supporting in this space is called Foro Energy, who is based in Littleton, Colorado. Foro's founders were troubled by the slow pace of innovation in clean energy, and they noticed that developments to improve a few percentage points a year in energy we're moving at a much slower pace than the rate we see in things like semiconductor chips and improvements in computing capacity that follow Moore's law. And so we ultimately joined forces with them to apply laser energy to invent a whole new generation of technologies for high-rate drilling and precision control of fracture networks in some of the hardest rocks on Earth. A lot of folks thought this was not possible, including a very smart Secretary of Energy. But they ultimately demonstrated the ability to transmit 7 megawatts per centimeter square, that's a lot of power, of laser power downhole and drill granite at a dramatically faster rate than has ever been seen before. And so with technology like this in our FORGE effort, EGS may be a lot farther along than many people think. And so one of my favorite examples of the ingenuity of our national labs is in the area of 3D printing. Researchers at our manufacturing demonstration facility at Oak Ridge National Labs collaborated with an innovative startup called Local Motors to design, develop, and prototype the very first 3D printed car, which was a 50th anniversary edition of the iconic Shelby Cobra Mustang. And what's remarkable about this is that none of the technology that was required to do this actually existed at the first day they started this initiative. The existing printers that we had were far too small and slow to build a car and would have taken thousands of hours to get there. And so Oak Ridge worked with a manufacturing equipment maker that had coincidentally sold equipment to Henry Ford when he was developing the Model T, so it's been around a long time. And within months, they had invented the largest and fastest 3D printer in the world. And it took a team of engineers that were then able to finish a fully functional electric car in only 6 weeks using that printer. And so you can see here the president and the vice president taking a peek at the car. It was recently displayed to all the world leaders at the COP21 as an example of cutting-edge technology that we're putting out to meet our energy challenges. You can hardly ever see the car on the road, but we still get a lot of mileage on it. It's probably one of the most highly requested things that we have in DOE to go showcase. And so I'm really envious of all the students that are here just beginning their careers today when we're starting to see so many real exciting developments in the field of clean energy just starting to take off. And I'm confident that we're going to look back on this moment as a major turning point for the transition to a global clean energy economy. It'll take all of us working together to get there, working in partnership across sectors to knock down the silos that hold back the progress and show great clean energy technologies that are able to reach the market and to get to consumers. And so that's why our team is looking forward today to learning more about the work that you do here and what we can do to contribute to this collaboration. And so I just wanted to thank you very much and conclude and look forward to taking some of your questions. Because I don't have the broad swath of knowledge that Dr. Danielson does, if there are any questions, we can defer them to some of our experts here as well in the audience. So, thank you.
We have a few minutes for questions. Yes, please.
Thank you for an interesting talk. Can you tell us what your view is on how much energy is required to make the batteries and how much benefit I got out of it?
How much energy is required to make batteries?
Or CO2 footprint?
Yeah, so we look at what we call cradle to grave analysis when we look at carbon. And so we started off with wells to wheel, and then we got asked the same question: how much energy and carbon does it take to make the batteries as well as to recycle them? And so all of our analyses that we have, and there's a study that we're about to publish called Cradle to Grave, looks at the entire life cycle of from mining to production to usage to disposal of all of our technologies. And so I don't have the exact number offhand, but I can probably come back to you and show you that even with the full production cycle of a battery, the net benefits of using electrification and transportation from a carbon perspective far exceed the amount of energy it takes to produce them in the carbon.